Whenever we have a problem, what's our first instinct? It's to find the best answer, right? The single perfect solution. But what if I told you that's kind of the wrong way to look at it? What if the real power isn't in finding one perfect answer, but in discovering every single good answer out there? Well, that's exactly what we're diving into today with a really cool idea in optimization called quality diversity.
So here's the plan. First, we're going to talk about why just looking for the best solution can be a trap. Then we'll get into what quality diversity, or QD, actually is. We'll see how it works under the hood, look at some mind-blowing ways it's being used in the real world, and wrap up by peeking into the future of this whole field. Let's get started.
All right, let's jump right in. To really get why quality diversity is such a big deal, you first got to understand the old way of doing things, and why it kind of puts us in a box.
So, think about it. What does optimize usually mean to us? It means finding the one single best result, period. The fastest car, the strongest material, the most efficient algorithm. It's all about that one winner-take-all global optimum.
A great way to picture this is to imagine all the possible solutions as a mountain range. Traditional algorithms? They're like climbers with a single mission: find the absolute highest peak, Mount Everest. They're programmed to just go up, 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 following the steepest path. The problem is, they completely ignore all the other really cool, maybe even more useful mountains nearby just because they're a few feet shorter.
But here's the thing, right? In the real world, that Mount Everest solution might be totally impractical. Maybe it's way too expensive, or you can't actually build it with current technology. In fields like engineering or design, you don't want just one answer from the computer. You want a whole menu of options. You want to see the trade-offs.
So that brings up a huge question. What if finding the highest peak isn't the goal at all? What if what you really need is a full-on topographical map of the entire mountain range? A map that shows you all the good peaks, the different trails to get to them, and everything in between. A treasure map of possibilities.
And that is precisely where quality diversity, or QD for short, comes in and just completely flips the script. It's a whole new philosophy for how we search for solutions.
See, QD algorithms aren't playing a winner-take-all game. Their job is to be a librarian, or maybe an archivist. They're trying to build a massive collection of solutions. We're talking thousands of them, where every single one is high quality, but they're all different from each other in some important way.
So let's break that name down. Quality is pretty straightforward. That's just how good is the solution. How fast, how strong, how efficient. But diversity, that's the magic ingredient. It's not about how well it works, but how it works. What's its style? What's its behavior? It's the how versus the how good.
And this image just nails the difference. On the left, you've got that traditional approach, just finding that one lonely peak. But look at the right. That's QD. It's not just climbing one mountain, it's lighting up the entire landscape. It's finding a great solution for every possible niche, every different type of behavior. It's creating a complete atlas, not just a pin on a map.
Okay, let's make this concrete. Imagine you're teaching a six-legged robot to walk. A normal optimizer would churn and finally tell you, okay, this is the single fastest way to walk forward. That's it. But a QD algorithm, in one go, it'll give you thousands of options. It'll find the best way to walk forward, sure, but also the best way to walk backward, to sidestep, to crawl, to tiptoe, to scuttle. You get this entire library of movements, a whole behavioral repertoire.
So how in the world do these algorithms actually build this incredible library of solutions? Well, the process is actually surprisingly simple and pretty brilliant.
Let's look at one of the most popular QD algorithms out there. It's called Map Elites, and the name tells you pretty much everything you need to know. The goal is to create a map and fill every spot on that map with an elite solution.
Okay, so here's how it works. It's basically a simple loop that runs over and over, like millions of times. First, you set up your map. It's just a grid where each little box represents a different kind of behavior, like say, walking fast with high steps or walking slow with wide steps. Then, the algorithm just cooks up a random solution, a new way for our robot to walk, and tests it. It figures out its quality, how fast it is, and its behavior, what box it belongs in. Then, it looks at that box on the map. If the box is empty, great, the new solution goes in. If there's already something there, it checks. Is the new one better? If it is, it replaces the old one. If not, it just gets tossed out. And that's it. You just do that again and again and again, millions of times, slowly filling up the map with the best of the best for each category.
And as this runs, it's not narrowing down to one answer. No, it's building out. It's creating this amazing, rich archive, this map of possibilities that just gets better and more detailed over time, filled with thousands of different high-performing solutions.
Okay, so it makes a cool map of solutions. So what? Why does this matter? Well, this is where it gets really exciting, because the real-world applications are absolutely incredible.
Take robotics, for instance. It's a total game changer. Imagine that six-legged robot we were talking about is walking along and suddenly, bam, it loses a leg. A normal robot would just collapse. Game over. But a QD-trained robot, it doesn't even panic. It just consults its internal map of solutions, finds the cell for best way to walk with 5 legs, and a few moments later, it's back up and moving. It's resilient, baked right in.
And it's not just about robots. QED is this incredible innovation engine for pure creativity. Scientists are using it to explore totally uncharted territory, designing these wild, alien-looking but perfectly functional 3D printable objects, generating novel images that no human would ever think of, and even discovering weird pictures that can reliably trick some of the smartest AIs on the planet.
But the key takeaway here is about empowerment. It's not about the computer giving you the answer. It's about the computer giving you a huge palette of amazing, high-quality options. It hands this collection over to a human designer who can then make the final call based on things the computer can't possibly understand, like aesthetics or elegance or how easy something is to build.
All right, so this all sounds amazing, but it's not without its challenges. Let's look at the future of QDLT and the huge hurdles researchers are trying to overcome right now.
That simple grid we talked about for map elites, it works beautifully if you're mapping out, say, 2 different features, like speed and leg height. But what if you want to map 20 features, or 200? The problem gets, well, it gets exponentially harder. This is what's famously known as the curse of dimensionality.
And when I say it explodes, I mean it explodes. Just look at this. If you wanted to map a space with just 50 different features using that simple grid, you would need, get this, over a quadrillion cells. That's a 1 with 15 zeros after it. Just storing that map would take 4 petabytes of memory. I mean, it's just no way. It's completely impossible.
So how do you solve an impossible problem? Well, you get clever. You make a smarter map. On the left, you've got that old, rigid grid that just breaks when you add dimensions. But on the right, you have the solution. Newer algorithms like CVT Map Elites use a totally different, flexible approach. Think of it like this. Instead of trying to build a grid with a quadrillion cells, you just tell it, hey, no matter what, I only want you to find the 10,000 most interesting and different solutions. It then intelligently carves up the space to fit that number, no matter how many dimensions there are. It's this kind of thinking that's letting QD tackle problems that are way, way more complex.
And that really brings us to the core idea here. Quality diversity is more than just a new type of algorithm. It's a fundamental shift in how we think about solving problems. It's about changing the question we ask our computers. Instead of saying, give me the best answer, we're starting to say, show me everything that's possible. Show me every good answer. And by asking that bigger, more open-ended question, who knows what incredible new possibilities we're going to discover?